what will happen is that I will go through the selected questions from the 2019 prelim. All right. So as much as possible, I'll try to cover some of the more difficult parts. But if let's say there is any questions that you have, you can consult our tutor later. The answers and the examiner report will be uploaded onto the Google Classroom at 6 o'clock later. All right. Okay. So this is the actual prelim question. So it's a full paper, 2.5 hours. All right, with a stimulus-based question and also choice questions at the back. So some of you have asked me, like, in 2.5 hours, how on earth am I going to finish this whole paper? So again, you must devise a strategy. All right. So your goal is to gain as many marks as possible. All right. Especially the questions that involves recall, especially the questions that involves basic practices and interpretation of the content, the syllabus content that you have learned. All right. So that is what you need to do. So the goal is to make sure that you are familiar with what is in the syllabus, what is in the lecture notes, what have been covered in the tutorial. In fact, I'll show you that this prelim exam, a lot of questions are actually what you have supposed to know. All right. And you just need to see and link it. Okay. And even some of these questions are actually quite basic. And so you should be able to gain as many marks as possible. So think of a strategy. All right. Your goal is to complete as many parts and questions as possible. All right. Within the 2.5 hours. Okay. That will be your goal. All right. Unlike your H2 paper, maybe you still have like 5 minutes, 10 minutes at the end to and then to check your answer. You might not have that luxury in the H3 paper. All right. Yeah. Okay. So because of the limitation I have with my devices, okay, since I'm doing this from home, all right. I will go through the insert first, and then I'll cover some of the questions that you might have encountered that involves the insert, and then I'll go back to the main document. I will cover mainly question 1, 4, 5, and 6. Okay. Question 2 and 3, I'll probably not spend much time on it. Question 8, if you have time, we can cover some selected parts. Right. That is my goal today. Okay. Now, the first thing that you see in your insert is, of course, this particular diagram. All right, which talks about nitrogen fixation. So nitrogen fixation, basically, bio students should have come across this term before. So basically, you want to take the atmospheric nitrogen and make it useful, okay, for any other purposes. So it's like making it a good source of nitrogen. All right. So plants are very good at fixing nitrogen. All right. It turns the nitrogen gas in the atmosphere, or rather, it is fixing nitrogen from, let's say, inorganic sources like urea. Okay. And gives us protein. All right. And of course, scientists does it in other ways as well. So here is a diagram that is related to some question. All right. So the first thing that you should notice is that MO diagram of nitrogen is familiar. Okay. This is actually the sigma. All right. This is actually the sigma. Let me change the color. Sorry. Okay. And this is actually the pi star. Okay. The pi star molecular orbital and also the sigma molecular orbital. So you should see later the question asks you to draw the MO diagram, all right? And you should be able to relate this. And then you realize that this is actually, HOMO, okay, based on the MO diagram that you have drawn. And this is actually the LUMO, all right? And you realize that this one is donating electron density from a bonding orbital. Okay, so this is a bonding orbital. And then this is an anti-bonding orbital. So the bonding orbital donates electron density away. Then the electron density is donated into the anti-bonding orbital. So what happened is that your nitrogen bond will be weakened, okay, because the electron density is added to anti-bonding orbital and is donated away from a bonding orbital. All right. So that's how you would try and imagine this question. All right. This diagram, and that's how it helps you to answer all the question. Now, then we'll move forward. One of the information that you might have missed from this part is this 10. Okay. So there's a 10 molar equivalent of the complexes. So when you do the calculation that involves the ruthenium, all right, so this is where the ruthenium is. It's actually 1:10 mole, okay? 1:10 mole ratio. And you might have missed that. Huh? So in calculating the amount that is required to produce 1 ton of ammonia, all right? So you have to work backwards and you have to work that this is 50% yield, all right? And besides the 50% yield, it also needs 10 molar equivalent of the ruthenium complex, all right? Okay, so actually these questions do not involve complex. You realize that it doesn't involve a lot of complex metals, all right? It's just normal calculations. Another thing that you might have be useful in your answer is this. The question asks you about the pKa of the complex, all right? And of course, the reason why you have the pKa there because of the hydrogen, okay? The hydrogen needs to be given away from the complex. That is the source of hydrogen for the production of ammonia. The source of nitrogen comes from this complex, and the source of hydrogen comes from the H. So the H needs to be easily given away. And if it's not, all right, then you will have a bit of a problem, all right, producing ammonia. Okay, so this is part of the question that you encounter in one of the parts. Another part of the insert, okay, let's scroll to the bottom. Okay. Okay, so then you have this particular diagram, all right, where you have a lot of different things going on, all right. So it is actually a cycle with step 1, step 2, step 3, step 4. One of the questions asks you to write down a balance equation involving all the steps. So you just have to follow, okay, what is given in this cycle, all right. So of course, this is the reactant, this is the reactant, then you get this as a product and this as a product. So that will be the equation for the step 1. And then you just list out all the equations, then you realize that some of the species cancel away, and then you can get the final equation, all right? Now, then you also will ask about this particular compound, okay, in step 2, where you will ask like, what is so special, okay, about this? Now, then you try and look at what is the reaction that is occurring. So if you look at this particular compound that's of interest here, all right, the product is actually methanol. So if you want to get methanol as a product, what you have to do is to get this out of the ring, all right? So, and what happened to the rest of the carbon, all right? The rest of the carbon is actually, okay, becoming part of this structure, okay? So the types of reaction actually is mainly addition, elimination, all right? Based on the structure, okay? Because you see that this is actually the O. It's as if like you protonate it, then you get the methanol. And you want to do something, all right, to make it leave, all right? So therefore, the likelihood is that you see the nitrogen is bonded to these 2 carbon. So some form of nitrogen attack would have happened on these 2 carbon as well, all right? And therefore, what it means is that your nitrogen, all right, is acting as a nucleophile. And interestingly, this nucleophile is positively charged. Okay, so that is what is so special, all right? So this molecule, this complex is acting as a nucleophile, but at the same time, it is a positively charged nucleophile. Okay, so that is what is so special about this particular step. Okay, next diagram, or rather next abstract, is a different way of fixing the nitrogen, all right? So then some questions that were involved here. One of the most common question is, what is CH activation product? Okay, maybe I scroll up a bit. Okay, so what about CH activation product? So based on the word CH activation, so it must be something to do with a CH bond. So then you try and find what has changed in converting B to D. Then you realize that what has changed, all right, is related to, is related to this part of the molecule, okay? So at the boron, all right? So at the boron, all right? So here, okay, you have the CB, all right, the CB bond, okay, being formed, okay, and you realize that the C double bond N has gone, and there's an additional H that is being added across, all right? So it means that this part of the molecule, the H is added, okay, and this B forms a bond. So where does the H come from? If you compare the two compounds, then you realize that the H actually comes from here, the end of the methyl group on top. That's where the H comes from, right? Because the carbon has to give up a H in order for it to bond to the boron. So this boron with the electron reach, okay, is like as if forcing the carbon to give up a hydrogen. So it's a way of activating the CH bond, all right? And this H, okay, can be of course added across to the C double bond N, right, to form the CH bond. Okay, so that's how I will see it. Okay, so that's why D is known as a CH activation product. Okay, so that is one. The other part of the question involves this diagram is of course the delocalization of this system. Okay, I assume that you've attempted all those questions, so that's why I can discuss in this way, and I'm not going to discuss question by question. So the question asks you to draw resonance structure. Then actually this whole part is a delocalized system. Okay, so how do you see that this is a delocalized system? All right, you see this boron is actually electron rich. Okay, it has more than 3 bonds. It has 4 bonds in fact. All right, so you can start by drawing a resonance structures there. Okay, so one possibility is to start at this boron. Okay, and you can donate this electron density, can donate this electron density, and you can let the N becomes neutral. Okay, so that is part of that. Never begin with this. Okay, please don't begin. Let me change the color. Please don't begin here. All right. Okay, because here the nitrogen is already positively charged. If you begin your arrow here, okay, what happened is that nitrogen would have gotten 2 doubly positive charge, which is not desired. They're not desirable. Okay, so not a very good idea to have. So basically what it means is that it's not an electron source. And in fact, the N with the positive charge is an electron sink. So what you should have done, okay, in drawing your diagram is to push the electron towards the sink, okay, where the N is the positive charge. All right, okay, so just something for you to consider. Okay, so yeah, the details of the answer you can of course check on your own. Just want to discuss conceptually. Okay, let me see if I've covered. Yep, okay, that's the end of the insert. Okay, let me switch the document now. Okay, so I have formatted my document such that the question and the answer is together for lecture purposes. You will get a separate copy, all right, or rather you'll get a separate formatting where you have only purely answer on the Google Classroom data. Okay, so I've explained, I mean, A1 is from your H2, nothing too special. A2, all right, so what is different in A2 from what you have encountered in your recent lecture test? Are the wordings too small? Do I need to zoom in further? I think should be okay. I hope you all can see. Okay, so what is different is that this question requires you to consider a bit more. Okay, so it requires you to consider, let me change my color. Okay, it requires you to consider this, all right? There is a swap in the relative energy level between the two sets of the highest occupied molecular orbital, all right? HOMO, okay? So you must see that this is a HOMO. So it's trying to tell you that, yes, you can draw the O2, but for the N2, there is a swap, okay, between the two sets of the highest of the HOMO, all right? So therefore, the resulting molecular orbital would be that the sigma and the pi, okay, swap position. Okay, so this question specifically tell you to do so. But in the lecture test that we had, we specifically tell you to not consider SP mixing. All right. So you got to read the question properly, all right, and answer accordingly. Okay. So this question tells you that there's a swap, okay. Okay, and you realize that this sigma was the one just now where, if you recall, okay, the orbital looks something like this. Okay. So with the nitrogen, all right, donating. So you got to link that, oh, this is actually the sigma orbital, and actually the sigma orbital for nitrogen is the HOMO and is donating away. And then in the diagram, also you have this diagram. Okay, so this is the pi star. Okay, and you see this is the pi star, and the pi star was shown with electron density donated. So donating electron density, and then this one taken away, of course, you will reduce the bond order and you will weaken the nitrogen. Okay, so that's how you answer this question and the subsequent part. Okay, so the calculation just now I already said, all right, the 10, okay, you got to check the 10 is there. Okay, this one I also mentioned already, all right, the pKa value, okay. Then you are asked to suggest 2 reasons why this is more useful. Now you realize that in this history paper, we model it quite closely to the specimen paper that we received from Cambridge the first year of the exam, all right? 2019 was the first year of A-levels that we have the new format and the new syllabus, all right? So we model this paper very closely to the specimen paper. And in that specimen paper, there were a lot of open-ended questions that requires students to think a bit more from the chemical principle point of view. So this is one of them, all right? So you suggest 2 reasons why, this process in abstract 1, all right, is more useful than the one shown in figure 1.2. So the figure 1.3 of the abstract 1 and figure 1.2, of course, they are slightly different processes, okay, and you are asked to compare them. All right, so that will be the answer. Of course, any answer that is reasonable, okay, any answer that is actually make chemical sense, all right, would actually receive credit. Okay, so this kind of open-ended question, there's no like really there's definitely wrong answer. Okay, there's definitely wrong answer, but then we can accept a range of answers. All right, okay, based on what you have written. Okay, so always this kind of question, right? You always think a bit in terms of like environmental friendliness. Always think of it like, is the product more useful or not? This kind of question, or you think like, how about the cost? Is it lower? Cost lower means that maybe it involves less reactant. Maybe it involves less number of steps. Maybe the chemicals are readily available. Maybe there's no need for heavy metals, so then you don't need to consider the waste, radioactive waste, for example. So these things, we cannot teach you explicitly, but from your experience of learning chemistry for the past 6 years, all right, these things, are the small little things that you have collected, from your past experience in learning chemistry, and these are the things that you'll be used, okay, to actually answer this kind of question. All right, so it's a bit of a common sense, but then it is based on sound chemical principle. All right, and that's what we try to expose you, right? Okay, in this kind of question. All right, and Cambridge definitely is actually loving to ask this kind of question. Okay, so for example, in this question, all right, I ask you to compare the 2 methods. Okay, and one is more environmental friendly. Okay, because you do not have heavy metal. All right, you do not need to consider heavy metal waste, and most of them are actually radioactive. Okay, then you can also say that, the other step is more useful because it produces a variety of functional groups. All right, okay, so rather than just rather than something that's not very useful. All right. Okay, so because the other one is just like and yeah, okay, so you just need to compare, all right, the processes. Okay, than the one shown in 1.2. All right, 1.3 you get a lot more variety of different products. Okay, rather than just the ammonia itself. Okay, move on. All right, this kind of oxidation reduction, I'll leave it to you to figure out. Part 3, I already discussed just now. Okay, so I already proved to you why is it so special. Okay, part 4 is just the writing down step by step, okay, in the cycle, all right, and then try and cancel off all the common terms, all right. You have done this in your recent lecture test as well, okay, with the mechanism of the 2 electron, 4 electron, 1 electron, WOF, okay, so here's also the same, all right, okay, so just need to do the same thing, okay, with the cycle. Okay, D1, this is just a recall question from your syllabus. Okay, so you need to know how or why certain nucleus is actually NMR active. Okay, so if you're not clear, please go and revise. And then the question asks you to explain the difference, even though it is boron NMR, something that you have not seen before, but doesn't mean that you cannot answer the question, because the question says, okay, their signals are affected, okay, by the same factors that affect the proton resonance. All right. So therefore, whatever you learn in your proton NMR, okay, can be applied here. All right. Okay. So yeah, why certain atom, sorry, the boron atom in D and E, they have different chemical shift. All right. That is related, of course, to how much electron density you have around the atom. Okay. So for protons, right, the more deshielded means that it is probably beside a electron withdrawing group. So it withdraws electron density from the proton, so therefore it becomes more deshielded, right? So here is also the same, okay? So if the boron is in a more environment that's more deshielded, or in the environment that is lower in electron density, okay, then of course you will have a higher chemical shift, all right? Okay, so I'll leave it to you to figure this out. Okay, this one I've explained already, all right, for what does the CH activation product means, okay, all right, so you just need to say something, you know, we don't expect students to be very accurate in this kind of higher order thinking question, all right, as long as students get the idea correctly, usually the credit is already awarded, all right, for this kind of question, okay, all right, you may use a diagram, okay, yeah, so if you can able to illustrate this transition state, good, but I think in the marking, of course, it is not necessary lah. All right, okay, but of course, it's always good to use a diagram, because a diagram really helps you to speak for 1,000 words, all right, rather than you writing. Okay, yeah. Okay, so then they ask you to apply the same concept onto the BF3. Okay, so the boron complex, not BF3, sorry, the boron complex, okay, is sp2 hybridized. Okay, so you got to consider again, just now in the figure 1 of your insert, right, if you have not noticed, it's actually a transition metal. So transition metal has d orbital, right? So those are the interaction between a d orbital of a transition metal and the MO of the nitrogen. So here you are trying to apply the same kind of concept, okay, but instead of having the transition metal, you have the boron. And the question says the boron is sp2 hybridized with the lone pair in the p orbital. All right, what it means is that you have learned this in your chem bonding, your H2. All right, actually a lot of things is all your H2. So yeah, my hybrid orbital is not nice. Okay, shouldn't draw it this way. I'll get scolded by my student. Okay, yeah, clear. Okay, okay. So okay, so I mean you should have already known how to draw your hybrid orbitals properly. Okay, so this case is a sp3. Oh, sorry, sp2. All right. So sp2 and the sp2, and then you have an unhybridized p orbital, right? And the unhybridized p orbital, of course, is perpendicular. Okay, so if I draw it on the spot here, all right, there's an unhybridized p orbital. Okay, oops, there's not that many electrons. Okay, so you have the unhybridized p orbital here, all right, with 2 electrons. Okay, so it's the same thing. All right, so the sigma and the pi star. So the sigma donates to the empty sp2 orbital, and the pi star gets the electron density from the unhybridized p orbital, which contains the lone pair of electrons, all right, which is actually written here. Okay, so you just need to check because the boron has how many bonds? Okay, you can check, all right, and it has two bonds with a pi bond. So that pi bond, right, the B double bond, the pi bond, the two electrons must be in the unhybridized p orbital. And then you have two more sigma bond. That means one of the sp2 hybrid orbital must be empty. Okay, and that empty sp2 hybrid orbital can accept a pair of electrons from the sigma, from the HOMO, basically, okay, of the nitrogen. And then the pi bond, which is the unhybridized p orbital, all right, which contains the lone pair, okay, is able to donate it to the LUMO or the pi star of the nitrogen. Okay, so you got to see all these relationships. So you got to see the molecule, and then you got to decide, okay, where the electrons are, okay, and the presence of pi bond means definitely you have unhybridized p orbital, okay, and you have the electron inside, all right. Okay, so then you got to decide, okay, so I have sp2, all right, so the sp2 must be, one of the sp2 must be empty, okay, because I only have two sigma bonds there, right? Okay, so all these things have to come to your mind. Okay, yeah, this is the resonance structure, okay. So the question said that it was represented as a delocalized manner, all right. So I'll leave it to you, okay. Just now I've already explained partially, all right, where the electrons are, okay, how do you begin and end, okay. So the details of the answer, I'll leave it to you. Okay, now, so then again, this kind of question, all right, open-ended question, okay. So abstract 2 does not use transition metal. As exciting as it is in the infant stage of study, it does suffer from some disadvantages, all right. So suggest two disadvantages of the second method, okay. So when you see disadvantage, what do you look out for? Again, those factors will come in again. Whether is it costly? Is it very complicated process? Does it require very high pressure, very high temperature, or does it require very low pressure or very low temperature? Does it require a lot of steps? Does it require a lot of expensive chemicals? Does it require some radioactive, heavy metals that might not be so easily available or might be costly to manage the waste, for example? All these things, okay, come into play again, all right? Or how useful the product is, okay? So then these are the same kind of chemical principles that the syllabus wants you to learn, all right, through your H2 and your H3 learning, okay? So in this case, all right, yes, good thing, all right, the second method, the abstract 2 method does not involve heavy metal, okay, or does not involve transition metal. But the problem is in this step, right, you realize that you need a very low temperature, all right, it has to be cooled to minus 80 degrees Celsius, okay, as stated, okay, and also it has to be kept in pure, some of the pure gases like CO, argon, and N2. So it's a bit complicated, okay, because the reaction has to be done in this kind of pure atmosphere, all right, okay. So it is a bit tedious, basically. So that's what you need to write about. And also, you realize that the product of the abstract 2, right, the product E, the product D, and the product C, it is just like that, okay. Whereas in abstract 1, you realize that at least you get things like ammonia, which is one of the most heavily produced chemical on Earth. It's one of the, in fact, ammonia was the subject of the question in 2019 A-level paper, yeah, in history, yeah. So ammonia, good, very useful. So anything that can produce ammonia is excellent, okay. At least in abstract 1, you also get other nitrogen compound like pyrrole. I saw pyrrole there, okay. So therefore, might not be very useful here because the complex is like, okay, so what? So what? I have fixed the atmospheric nitrogen. I convert it into some form of complex, but then doesn't seem to be very useful at this moment of time. All right. So that is what you can argue, okay, that there is no useful products, okay, that is being formed or obtained in this particular process. All right, in abstract 2. So you see, it's very open-ended. The answer is not extraordinary. It's not like, wow, very cheap kind of concept that you need to know. Like you have to bring in all sorts of very weird, or not weird, but very deep knowledge of chemistry. No need, all right? It's really basic chemical principles that is a bit of like, this is common sense, but yes, this is the common chemical principles. You know this because you have been learning chemistry for many years, and you are required to actually gather these knowledge back, all right, and know how to apply them in a context that is foreign to you, all right. But you realize that you have some sort of 成就感, sense of satisfaction, because you realize that, hey, I didn't learn chemistry for 6 years for nothing. At least, I can guess a bit of this kind of actual industrial process and how is it useful, in applying them. Okay. Yep. So that will be my discussion for question 1. Okay, let's move on, to question 2, all right. Oops, okay, never mind. Okay, so question 2, I will not go through them. I think it's quite a simple question, all right. So you can look at your answer later when I upload this, so I will not go through them. Okay, question 3, I will also not really go through them. Oops, okay, because question 3 is also relatively simple question, all right? Just applying what you learn from your syllabus. Okay, maybe you might be scratching your head about how to do part A, all right? The reason is very simple. You totally forgot the learning outcome of Bell's-Evans polyanion principle that you have learned in your syllabus, okay? So we have not tested this in our lecture test this year, okay? But please make sure you see this, you know what is it, because this is what is in your learning outcome, it is part under the chapter on Hammond's postulate, the basic physical organic chemistry. So if this doesn't ring a bell, or if you don't know how to do question 1A, all right, something is not right, you should go back and recall this. So this is just purely recall question, nothing too special. Then after that, you are supposed to sketch that, and the question asks you to sketch based on Hammond's postulate, all right? So, and the question already gives you quite a number of information, based on this part as well. They give you the EA, they also give you the delta H, all right? So you should be able to sketch, the energy profile diagram correctly with the corresponding sign of the EA and the delta H for the two, for the different steps, all right? Okay, so make sure you know how to draw transition state. So transition state is really showing how bond has broken and bond formed. So if you recall, based on what you learn in your H2, you do something like this, Let's say this one, So in your H2 syllabus, what you do is, I'm going to attack this. Then after that, what I'm going to draw is usually something like this, NO2, and then I'll draw like this, and then I'll draw a positive. Then your teacher will tell you that the semicircle must cover at least 5 carbon atoms. What does it mean? All right, it means that the electrons are actually delocalized, inside, inside the benzene ring. All right, so here is also the same, They're just trying to ask you, in the bromination, all right. In this case, what happened is that you have a this one, you have an ether, with the lone pair, and then you are supposed to attack a Br plus, so of course that Br comes from your adding of the Lewis acid, so then what happened is that this is the H, so this is the part where it will attack, and of course you have to draw, the pushing, arrow pushing from the lone pair on the oxygen, all right? So then what you get is you get a product that is something like this. Double bond O, and then this one, and then you get a H, and then you get a Br, So what you want to illustrate is the transition state, So this transition state, all right? So you realize that actually the electron density, is delocalized in the system, So therefore, you have the bond breaking and the bond forming dashed lines, right, that is being drawn on it, So recognize where are the bonds that are about to form, where are the bonds that are about to be broken, and recognizing that the benzene ring is a delocalized system. So you are breaking the delocalized system in the process of attacking the Br+. So in this case, the bond is forming. In the ring, the bond is breaking. In the CO, the bond is forming. All right. So you see, the bond is forming. The bond is breaking because you are breaking the aromaticity, and the bond is forming between C and Br. Okay. So that's how you draw your transition state properly. All right. Okay. With the dagger, some of you ask me what is the dagger. All right. The dagger is just a sign for transition state. Huh? Okay. So, and then you just need to, based on the Hammond's postulate, all right, recognize that whether is it early transition state or late transition state, okay, for this question. Okay, then the rest are H2. Okay, so part B1, B2 are all H2, so nothing too special. Okay, you should know how to do this question. Okay, question 4. Question 4 is also modeled very closely to the specimen paper that we have received from the Cambridge. All right, question 4, you already have your diagram with you, so I'll just zoom out. Okay, so basically this question is comparing two different routes to produce the same compound. Okay, so the compound that you're interested here is called the lycurine, all right, and it is either route 1 with the step of numerical A 1, 2, 3, 4, or route 2 with the step in terms of step A, B, C, D, E. Okay, so don't be confused. Okay, it's actually two routes producing the same compound, and the reagents and conditions and the yield was given in the table form. All right, which is exactly what Cambridge gave us that year. Okay, so the thing is, a lot of information were given to you. Some information might not be very useful. So sometimes don't spend too much time trying to understand, wow, what does all these things mean? Okay, don't worry too much. You just glance through it, right? You should be able to get a rough idea of what are the reagents and conditions used, and then move on. Okay, sometimes students spend too much time hopping on something, and then you find yourself and not enough time to complete the question. Okay, so like step 1, okay, I think is quite simple. Okay, I think you all should be able to get this. Okay, so by now I hope that you have seen enough to know that NaH is basically a base. All right, why is it a base? Because it contains H minus. Okay, all right, so it is a base. Okay, because it contains the H minus. Okay, so this H minus is acting as a base. It cannot act as a nucleophile. Okay, so think about it. Okay, so it's acting as a base in this NaH. All right, and so therefore, okay, if you look at what is B, okay, B has this C8H8ONCl. Okay, so it is added to this compound first before it's added to A. So B must have contained something that is acidic. Okay, so if you look at the structure, all right, of this, okay, so you'll notice that what is active, or what has changed from A is of course the additional of this part. All right, okay, and Br is gone. Okay, so when you see Rx, Br, please, okay, think of SN1 or SN2. Okay, or since this is all right an Rx. Okay, so means that it must be nucleophilic substitution. So something that's nucleophilic must have attacked the carbon inside the bromine. Right, so then you want to create the nucleophile. So it means that since it's a carbon nitrogen that is being formed, that means the it must have come from the nitrogen. Okay, so based on that, okay, and you try to compare the molecular formula, you realize that, all right, this should be the compound. Okay, where you have already learned that amide in H2, you learn that amide is neutral. All right, but of course in H3, we have the further understanding that amide is actually acidic. Okay, in the presence of a strong base. Okay, so a strong base like NaH. Okay, this is a strong base. Okay, so this strong base is able to take the H away, because after taking the H away, it can be stabilized by the C bond O. All right. Okay, so these are the basic things that you encounter, or you should have encountered many times in your tutorial. Okay, so part 2 is just your H2 syllabus. Please remember, in your H2, there is a learning outcome that you need to know, which is the reduction of amide. Okay, amide is reduced or can be reduced by lithium aluminum hydride. It is in your H2 syllabus. Okay, don't forget about that. Okay, part 3, again, this kind of calculation based on the yield. Okay, so each of the step has a different yield. So what you need to do is you are supposed to compound. So it's like a compound yield. So you multiply the yield together. I mean, if you cannot think of it this way, you just calculate it step by step. Then you realize that actually in the end, you are just summing the different yield. Okay, you are just taking 100 over 99 times 100 over 81 times 100 over 41 and okay, because you are trying to gain back, okay, what is the original amount that's required based on the different yield of the steps. Okay, all right, so I'll leave this two calculation to you. So interestingly, root 2, the mass of A required is much less than root 1. Okay, all right, so in root 1 you need 200 grams to produce the same amount, which is 50 grams of the lycopene. All right, so root 2 has clearly one advantage here, which is that the amount of A that's required, the mass of A that's required is less than root 1. Okay, so something to bear in mind. Okay, then after that, the question asks, apart from the overall yield, suggest 3 other factors that need to be considered when choosing a particular synthetic route. So again, open-ended question. Again, the same kind of chemical principles comes into play. So it's always all these things, all right? It's always these things that come into play. You see, again, cost, all right, whether expensive or not. Availability of the starting material. Do I just use water or do I have to use a very complicated complex, okay? Time required means that does it need more steps? Does the reactions is very slow, okay? All right, so if you have more steps means you need more days, okay, or more hours, all right, to produce the same product. Okay, does it need, very complicated process like in a certain atmosphere? Does it need complicated equipment, like very high pressure, very low temperature, things like that, okay, need to consider. Ease of separating, this one is also very interesting because if you have a product, if the product is in a solid form, or rather what you get is a solid and a liquid, then it's very easy because you just need to filter, then you can separate the solid and the liquid already. But if both of them are in the solution form, then you want to separate the impurities with the product, then it might be a bit more difficult. Or if let's say the impurity is inorganic, whereas the product that you want is organic, then it's also very simple because you can do a kind of separation. Okay, you can use an organic solvent, then the organic molecules will dissolve in the organic solvent, whereas the inorganic molecule will remain in the aqueous, and then you can do separation, all right, because the organic and the aqueous layer do not mix, all right, they are not miscible. So these kind of things, if you ask yourself, actually you know, you have learned it, all right, but you have never think of it in this manner to apply it, all right, to this kind of context. Toxicity of the reagent, right? Heavy metals, okay, transition metal, useful intermediates of products, okay. So all these factors, all right, comes into play, all right. So, 来来去去, okay, it's always these few factors, that is usually we will encounter. Another thing might be environmental friendliness, for example. All right, yeah, okay. So any reasonable answer, of course, will be accepted. Okay, so then part B. So ask you, how come you can have how come this particular hydrogenation in step 3 is selective? So if you look at the synthetic route, this is the benzene, okay, that is actually is reduced, all right, to become sort of a cyclohexane, all right. So how come is the carbon 7, 8, 9, 10, 11, 12 that is affected, but not carbon 1, 2, 3, 4, 5, 6? So what is so special about those carbons? So first, you must recognize the question asks you bond angle. So what is the supposed bond angle of benzene? Okay, you should know. Okay, since each carbon in the benzene ring is sp2, okay, so the bond angle should have been ideally 120 degrees, all right, because it's a trigonal planar sp2, so 120. So it means that any deviation from 120 is a strain. So if you look at the bond angles that's given to you, all right, where are the worst deviation? 125, okay, very, very bad. 122 is already one of the worst, okay, in the whole system. Where else? Not just positive deviation, but also negative deviation, okay. 108, you see there are 208s, okay, in these carbons, all right. Yes, you have 108 here, all right, but it's only one or two, okay, but you have this 125, 122. Those are major deviation from 120. So you look at the atom, 8, 9, 10, 12, 7, 8. Yeah, lor. So 8, 9, 10, 12, 7, 8. So it's always, these atoms, they are around, they have the greatest deviation of the bond angle. All right. So therefore, by that means that those bonds there, all right, those CC double bond there might be weaker, or by having it reacting with the H's, all right, you might relieve some strain in the bond because so therefore it is more reactive. Okay, so therefore it is selective at that particular place. So the answer, all right, is the deviation from the ideal bond angle in a benzene ring. So therefore it introduces strain, and therefore you have this pi bond. All right. Okay. After I finish this question, I think need a break. Okay, part C. Part C. Okay. So how do you analyze part C? Okay, so let's go back to the diagram. Okay, step B. Okay, I'll prove to you that you have seen this in your lecture notes. Okay, so in step B, okay, what happens is that you want to convert D to G. And the question says that the very first step is to add a hexanone, okay? All right, cyclohexanone, okay? So think of it, when you add the cyclohexanone, which part of the molecule is being formed? Okay, if you try and look at G, right? Where is the ring? The ring is actually here, okay? This is where the six-membered ring is introduced, and it's introduced with the formation of CN bond. Okay, so it means what? It means that this carbon here, which is this carbon, must form a bond with the nitrogen. And that nitrogen, how does it react? Of course, it has a lone pair on the nitrogen, and this is a C double bond N. All right, so in summary, if I put it out, right, it's basically a reaction of a primary amine with a reaction of a ketone. Have you seen this before? Yes. Okay. This is in your lecture notes. Okay. It's in your mechanism lecture notes. It's under the addition elimination part of the, no, it's under the nucleophilic addition part of the lecture notes. All right. So please go and revise. Okay. So if it looks foreign to you, you shouldn't. Okay. It's just a reaction between a primary amine and a carbonyl compound. Okay. Let's say in this case, which is a ketone. All right. Okay. So it should be in your notes. Okay. So therefore, you should recognize that the amine is actually able to react with the cyclohexanone. And so therefore, the second reactant, okay, of course, will involve this part of the molecule. All right. So then the second reactant, okay, must have reacted with this. From the molecular formula, you could even guess what is the structure, because there's a chlorine, all right, and the rest are all matching. So it must have been an acyl chloride. Okay, so then it must have a Cl there. Okay, so that's how you analyze this. Okay, so try and link to what you have learned. Okay, so based on that, the answer, all right. So with the reaction of cyclohexanone, you get this, okay, which you don't tell me that you have not seen this particular functional group. Okay, it's in the lecture notes, all right. I think I've mentioned this many times to students, okay, saying that this C double bond N is in your lecture notes, all right. Please go and look at it, okay. Then this, of course, is the Cl, okay, based on the molecular formula, all right. the rest of the things match to the product except the Cl, and the Cl, of course, probably is from the acyl chloride, right? With the HCl as the byproduct. Okay, all right. So this is just something for you to think. Okay, or if you can see the intermediate E, okay, gives you a hint as well, right? The intermediate E has only 2 oxygen. Okay, that means that the intermediate E has not, you have not introduced all these parts of the molecule that contains lots of oxygen, right? The 2 oxygen comes from the original compound. Okay, so those are the hint to let you see like what are the reactions that has happened here. Okay, C2, this is the part that most students will find difficult because you don't know what to do, okay, with this mechanism, all right? So suggest a mechanism to convert H to K given that J is formed in the cause. So H to K, right? And J is formed. We don't care about K first. Let's care about H to J first. So from H to J, what is the difference? What has changed from H to J? So very first thing is you realize that this part of the molecule has gone. Okay, this part of the molecule has already gone. Okay, has already been removed. And then you also realize that there is a bond that is formed between this carbon and that carbon. Okay, so that you form the 5-member ring. All right. So therefore, this gives you some idea on where to begin the mechanism. All right. So the first thing that you need to do is get rid of this. Get rid of this part of the molecule, and then form a bond. In fact, some of you, if you see this, right, you might think this way. The most direct thing to do, of course, is this. You look at this like, hey, you know, I can do this. All right. So there's a hydrogen here. Okay, that hydrogen is gone. Of course, I don't care about it first. I just attack this double bond onto this carbon. All right. And then I just eliminate this. Okay. So good. You already have some idea of what has happened. Okay. So this is, of course, some preliminary idea. All right. But for this to happen, might not be so easy because it's like not the activation energy is very high for this particular way of reacting because you are expecting things that are very far away to react, okay, and the electron density here might not be as great, all right, to attack. So there should be an alternative better way of reacting. So what is the alternative better way? You know that you need to eliminate this part of the molecule, okay? So instead of jumping from the cyclohexene ring, there is actually a better motivation here, which is the oxygen with the lone pair. That oxygen with the lone pair is able to form a pi bond, all right? Okay, and you must remember, formation of pi bond is always very favorable in eliminating things, okay? So in this case, by forming a C-O pi bond, all right, okay, it gives you a motivation to eliminate this part of the molecule, all right, and you gain a neutral molecule. Okay, you gain a neutral molecule. Of course, you can also, push the arrow to the O, then you get the O minus, O plus, BF3. Okay, some of you might have done this. Okay, you eliminate it, then you get the O minus, but you have to straight away recognize that this is actually not the best structure. Okay, given that there's a electron source and electron sink. Okay, given that you can just do this, and then you can make the oxygen neutral, both oxygens neutral, you reduce the formal charge, all right? Okay, so you get this, which is definitely a more desirable, okay, product, all right? Okay, than the one that has everything positive and negative, all right? Yeah, so that will be the first step, okay, to obtain. And then after that, of course, at the you would get a C-O, and then you can do a further attack. All right. Okay, I'll show you the answer now. Okay, so this is what has happened. Okay, so the first step is to eliminate this part of the molecule by forming a CO double bond. Sorry. Okay, let me just expand it. Okay, then after that, okay, get rid of this thing already, of course, then the best thing, the easiest thing to do is to attack the carbon to form the 5-membered ring, all right? Okay, and it must come from the electron source, which is on the lone pair on the nitrogen, okay? So after that, you just have to eliminate the H away, then you will get this J already, all right? Okay, and then you just repeat the process, okay, of eliminating this portion of the molecule. The same, you see, it's the same functional group, all right, ester. Here is also an ester. So since this ester is eliminated in this way using the the BF3, so given that there's another ester here, you should be able to eliminate using the same way with the BF3 as well, all right? And then you get the product. Now, of course, you must you tell me, Mr. Lee, very difficult, man. How do I get this mechanism? All right. It's okay. Okay. All right. Try your have some idea. Okay. Have some idea. Okay. So, mechanism is not a very easy thing to do. All right. That's why it doesn't carry a lot of marks in your A-level exam as well. Okay. But try and pick up. Okay, these kind of little things, even though your steps might not be perfect, but you should know that there's some idea that, okay, I need to do some nucleophilic attack, I need to eliminate this part of the molecule, how do I do it, right? Yeah, so try and consider these things. Okay, of course, mechanism, if it's an unfamiliar mechanism, sometimes might not be so easy to get marks. Then if you think that there are other questions that are easier to be attempted, go ahead. All right, come back later. Okay, so to do the mechanism. Okay, the last part, okay, which is part D. All right, so again, open-ended question, nothing too special. All right, so based on the factors that you have written, so can you decide whether you want root 1 or root 2? I would say root 1 is a better one because in root 1, okay, you have fewer steps. Clearly, you have fewer steps. So therefore, the process can be quicker and you have fewer reagents that are needed, okay? But of course, root 2 also has certain advantage, all right? So the yield is better. That's why you don't need so much of an A to begin with, okay? However, it also has more complicated procedure with a bit of if you look at the kind of procedure that's needed, the temperature, the equipment might be more complicated. But the answer, okay, of course, you can choose either root 1 or root 2, all right? Okay, so you would still be able to get the marks correctly. This is the exact mark schema from Cambridge, all right, that we adopted. Okay, I think let's continue. Okay, so let's continue with question 5. Question 5 is actually not that difficult, okay? But I don't know why a lot of, at least those from my class, they seem to have a bit of an issue with question 5, okay? Okay, so question 5 is basically a question that is mainly focusing on spectroscopy, all right? And you're supposed to figure out the structure of A and B separately, okay? And then after that, you think of how you can combine the two together. Okay, so A, all right, has some properties here. So I'll just write it down very quickly. So first of all, it reacts with sodium carbonate, all right? Hello, okay, don't forget your sodium carbonate only reacts with CO2H, all right? It does not react with phenol, so you shouldn't be proposing phenol for sodium carbonate. Okay, this is your H2. Okay, so, and it has a molecular ion peak at 128. Okay, so that is the first information that you get. It must have a CO2H group. Okay, and of course, you're not given a molecular formula, all right, but later you realize that you can actually guess that. Okay, so based on the mass spec, what can you have? This is a very simple and direct mass spec. Okay, if you don't know how to interpret this mass spec, I suggest you please go and revise your mass spec. Okay, because this is actually a basic interpretation. How do I know it's a basic interpretation? Look at this. All right. Okay, 128, 130, 132. This is m plus 1, m plus 2. Okay. And then if you want, you can take a ruler, but if they arrange it so nicely already, definitely it's 961. Okay. Another hint, of course, is you can try and see 9395. All right. Okay. So if you try and figure out this, you realize that this is 3:1. All right. It tells you that this particular compound has 2 chlorine atoms. Okay. All right. Okay. And that's all. Okay. That you can get now. Okay. So it has 2 chlorine atoms, and you are told that it has 1 CO2H. Okay. And then the MR is actually 128. So a lot of things can be solved already. This is already 70. Okay. This one is already 16 plus 16, 32. 32 plus 12. 32 plus 12. 32 plus 12, 44 plus 1, 45. Okay. So 70 plus 45, 7就是11, so it's 115. All right. So you are left with 13. What else can 13 be? Okay. Given that this is an organic molecule, so this is actually 1 carbon and 1 hydrogen. Okay. So basically your structure is CO2H. All right. And only 1 carbon. So it's H, H, and Cl. Okay. That's it. Oh, no. There are 2 chlorines. Okay. So 2 chlorines. Okay. All right. So that will be the answer. Okay. To structure of A. All right. Okay. So the structure of A should be a carboxylic acid. Okay. With CHCl2. All right. Okay. So that will be for this. Then the question B might be slightly more difficult because it's something that is not exactly in your syllabus. All right. That you need to read and interpret the information that's given to you. So first, they give you something that you're very familiar. All right. Assuming that HB and HC are chemically equivalent. Assuming that HB and HC are chemically equivalent. All right. Okay. You already know how to predict the spectra, because if you were to see the signal for NMR signal for HA, it is going to be a triplet, right? Because there are 2 neighboring protons, n equals to 2. So it should be a triplet. So then the information is trying to tell you how you can derive this triplet. All right, triplet is something like this. It has to be 1:2:1 ratio. Then it's called a triplet. Okay. So the question is trying to teach you how to get this triplet, okay, based on this coupling constant thingy. So if HB and HC are chemically equivalent, means that they are the same. That means that they would interact with HA in the exact same manner. So that's why they have the same coupling constant. Because coupling constant measures how much it interacts. All right. So if they have the same coupling constant, means that they interact the same way. Okay, exactly the same manner, all right, to the same extent. So therefore, they are the same. So then you are given the tree diagram on the right-hand side to prove to you how you get the 1:1 triplet. So it turns out that what you can draw is a tree diagram like this. So first, what you want to know is what is the shape of the signal for HA. So HA will couple with both HB and HC. So we will do the coupling one by one. So when it couples with HB, all right, it has a certain coupling constant of JAB. Okay, so we'll just, draw a JAB. So this is the coupling constant JAB. All right, and it couples with HB, so to a certain extent. Then after that, it also couples with the C hydrogen. So it has another coupling constant that is the same, which is JAC. So HA couple with HB, you get, this is a doublet. Okay, so if there's no HC, then you get a doublet, all right, with 1 neighboring proton. But because there are 2 neighboring protons, they are equivalent. So you continue to interact with HC and you interact with the same magnitude of the coupling constant. So what happened is that since this is JAB, right? So each side is JAB divided by 2. And since this is JAC, it's the same. So therefore, you expect this to be also equals to half of JAB. So therefore, what happened is that yes, you have one side that is of this, but when you draw the other side, right, it is double the magnitude. So that's why you got a 1:2:1 ratio of the NMR. Okay, so it's all about the coupling. So you got to understand this, otherwise you will not be able to proceed with the second part. Although whether you understand this properly or not, actually it does not really affect your interpretation of the mass spec in the subsequent parts of the question. Okay, so yeah. Okay, so again, HA interact with HB, you will get a doublet. Okay, but of course it also will interact with HC, and because they are all okay, the neighboring proton. All right, and since HB and HC are chemically equivalent, all right, so you will interact further, but with the same extent. So you get a 1:2:1 ratio. All right, where this number, all right, the coupling constant is exactly the same. Okay, so it's as if like this is half and half lah. Okay, so then you get, yeah, so that's how you try and recognize this. Okay, so what if the situation is different now? What if HB and HC are non-equivalent? That is what the question is trying to illustrate to you in the next subsequent part. What if, let's say, okay, you have a H3, all right, okay, and this is a chiral carbon, okay, and what if I have a H1 that I'm interested in, okay, so H1 here, all right, okay, it will couple with H2, it will also couple with H3, all right, and why it will do that? Because this carbon is chiral carbon, and the question says that with the presence of chiral carbon, H1, H2 are not chemically equivalent. Okay, so if they are not chemically equivalent, they will couple with each other. H3, of course, is not chemically equivalent with H1 and H2. So from the point of view of H1, it will couple with both H2 and H3, but with different extent. So when it couples with H2, it is 15 hertz. When it couples with H3, it is 6 hertz. All right. So then the question asks you to illustrate the splitting pattern with the aid of a tree diagram. So how do you do that? So do the same thing lah. You do it one by one. All right. So you do it by starting with H1. So I will do H1 couple with H2 first, and then I'll continue the tree diagram to couple H1 with H3 second. Okay. So then you start the tree diagram. All right. So you begin by having, if it is alone, no neighbor, then I have a H1. Okay. So since I have a neighbor of H2 and it's 15 hertz, so I'll just do this. Okay. And then I will do the same thing. And this is 15 hertz. All right. Okay. By having it coupled with H2. Okay. All right. Then not enough, because besides coupling with H2, I also couple with H3. And the coupling with H3 is 6 hertz. 6 hertz is less than 15. So therefore, if you look at this, all right, if you are going to couple further, okay, it is actually 6, all right, this is actually 6, which is less than the half of 15. Okay, so you also have this, and then you have this, okay, and this is 6, all right, less than half of the 15. Okay, so then what you get is actually a signal where you have 4 of the same intensity. This is not a quartet, because a quartet, the intensity must be 1, 2, 2, 1. The quartet intensity must be 1, 2, 2, 1. Here is a doublet of a doublet. So that's why the intensity, if you see the intensity, the height of the line is all the same. So the intensity of the signal is actually 1, 1, 1, 1. All right. So it's not the quartet. Quartet that you have learned is something like this. This is a quartet. All right. The intensity is 1, 2, 2, 1. Okay. But this is not the case here. Okay. So a case here is actually 1, 1, 1, 1. All right. It's a doublet of a doublet. That is the answer that is required. Okay. Here. All right. Okay. So the important point that you might have I mean, you can go home and think about this again, but what you want to actually discover is that this is exactly half, 7.5, this is 7.5. So because this is 7.5, okay, so this is only 3. So it will not go past the 7.5, okay? So therefore it will be narrower. Unlike just now, where it's just nice, the same, so therefore it would add up, okay? Yeah, so think of this particular tree diagram. So this is a question where you require you to think a bit more, but actually it does not affect you. If you cannot answer, don't worry. As you continue with the part on the structure elucidation, you can still answer the subsequent part. Okay, so then this structure elucidation is not that difficult, but also not easy, all right? Actually, you can just, actually it's not that difficult to get marks. Okay, in fact, I think if you cannot get the structure, most of you should be able to get at least all the interpretation marks that is on offer in this question. So the first thing that you look at the mass spec here, so try and see what information that you can gather. First of all, there's a very useful information that you can gather here. 77. Okay, that enables you to calculate x. Okay, that enables you to calculate x. And once you can calculate x, you can calculate y, because you are told that the m over z is 212. All right, and you already know that it's as N2O4. So 7p to 7, you know what is x, you'll be able to calculate y. So then you have the molecular formula. Turns out that the molecular formula is C9H12, okay, N2O4. All right, x is 9, y is actually 12. Then, of course, they tell you that you have mass spec of 612281. At this moment, it gives you no useful information just yet. Okay, then we look at the NMR. So the NMR is slightly more interesting. Okay, so let me erase certain parts. Okay, that are so that. Okay, I'll keep the molecular formula then. Okay, so let's look at the NMR. So the NMR is very interesting. All right, so what you should know from the NMR, based on what the question wants you to elucidate, right? The question says that try and elucidate this signal, as well as this signal. Okay, so they never ask you to talk about 3.45. All right, that one is just for you to reference. Okay, and you realize that the 3.45 looks a bit like what you had done in the previous tree diagram, but that's not what we are going to do today. Okay, so of course, first thing you have to recognize is that, wow, so nice, the symmetry. And given that this is 7 and 8, okay, this is definitely from the benzene ring, 4 aromatic protons, di-substituted benzene ring. And given that it is symmetrical, it is very likely that it is a 1,4 di-substituted benzene ring. All right, okay. So true enough, you see the proton is actually 2 and 2. So it means that you have 4 aromatic protons. Okay, so what else? Look at this, all right? So it's a CH, okay? All right, because it's only 1 proton. And then you have a doublet, okay? So it means that it is actually beside a CH, okay? Then you look at this part, also 1 proton. That means it's a CH and it's a triplet. So this is beside a CH2, okay? So you have the fragments, okay, that comes out from the NMR. So you already elucidate most of it. How do you know? Very, very simple, all right? So after you've done this, right, always go back to the molecular formula. I tell you, molecular formula is very useful, okay, sometimes to consider things. So what can you come up from the molecular formula? Look at the carbons. Benzene ring has 6 carbon. This part of the molecule has 2. Then this part of the molecule also has 2, but cannot be because the total number of carbon atom is 9. So benzene ring take out the 6 already. Then the fragment take out 2. So it must have 3 more carbons. It means what? It means that this CH2 is actually linked. It's actually linked. All right. So you already have multiple fragments come out already. Okay. You already can guess that because there's only 9 carbon atoms, these are the only possibility. So then you can say that, oh, I'm going to have a benzene ring and I'm going to have a CH2 carbon chain somewhere in the structure. all right? Because there's only 9 carbon atoms, okay? I've accounted for all the 9 carbon. Then you have 12 hydrogens, all right? So do I have account for all the 12? Yeah, I check. 1, 2, 4, 5, 6, 7, 8. There's only 8 hydrogen on the NMR. Means what? Means, okay, something very important. I got 4 labile proton. Because I only have 8 protons on the NMR, that means 4 has gone, okay? All right, so I have 4 labile protons that is not accounted for. So that makes your job very easy already. 4 labile protons, or likely maybe it is part of the OH, or part of NH, or part of NH2, okay, who knows, all right? Okay, so I need to have these 4 labile protons, must have come from one of these things, all right? And also you look at the way it is dishielded, all right? This one is, this particular signal is close to 5. So likely you have some oxygen around it. This one is only 3. Maybe it's beside a nitrogen, I don't know, all right? But it could be a combination, okay, of some form, all right? So therefore you realize that, hey, actually I have oxygen, I definitely have oxygen and nitrogen on my carbon chain because, you know, it is all affected, okay, one another. So based on that, right, okay, you will be able to more or less sort of guess what is the actual structure of the molecule already. All right. Okay. So that's how you analyze. Okay, a quick one. Okay. So of course, in the exam, you don't have the luxury of time to do. You have to answer the question at the same time. All right. What do I mean by that? Okay. So if you look at this part 1, we ask you to calculate X and Y. So whatever that I do just now is for you to calculate X and Y, right? Then part 2 is just a recall question for the NMR, right? So I will not go through that. Part 3, all right, I already deduced for you just now. Reminder, all right, in the NMR deduction, you need to have 3 things, okay? Deduce the number of neighboring protons, which deduce the chemical shift, deduce the splitting pattern, and deduce the integrating ratio, all right? So this is to deduce the integration ratio, all right? This is to deduce the splitting pattern, and this part is deduce the chemical shift, okay? So you got to have all this information in your deduction in order to gain the marks. Okay, so yeah, so I've done all this deduction just now on that particular diagram. Then now the suggestion of the fragment of 122. So how do you figure out this fragment of 122? All right, let me, okay, I open another document, let me check the data because I cannot scroll up. I don't want to scroll up. Okay. Okay, so okay, you are given the mass spec. Okay. So you are given that the mass spec is this. So you have the the M over E molecular peak is 212, and then 181, okay, and then 122, and then 60. All right. Okay. So then you try and figure out the difference. Okay. So just now I managed to do something, but I think my case gone. Okay, never mind. So what happened is that then you got to figure out the differences. All right. Okay, so 212 to 181. Yeah, I lost my working. Okay, never mind. So this is actually 31. All right. Okay, so 31. So you try and guess. Okay, then this is actually 59. Okay, so yeah. Okay, and then you can also try and figure out 212 to 122. Okay, this is actually 90. All right. So then you try and see where's the benzene ring. Could the benzene ring be in the 90? So you can try. Okay, given that you know it's 1,4 substituted, so you can try having the 90. So 6 carbon atoms with 4 hydrogens. All right. So this is partly. So then this accounts for 70. 76. Okay, so if this accounts for 76, you need another 14. Okay, to reach 90. Then you think 14 cannot be a nitrogen alone. What if I have a CH2? Then you realize that it cannot be this particular fragment. Why? Because this 90 is M minus 90 left. Okay, how can the M minus 90 be a CH2 like this and then be this? All right, so because usually the first fragment that is gone must be like a nice complete structure, right? This is definitely not. So therefore, it sort of gives you the hint that the 90 does not contain the benzene ring. If that is the case, that means 122 must contain the benzene ring. All right, and true enough, that 122, if you try to minus the benzene ring, you are left with 46, and that 46 corresponds to the NO2. All right. So that's how you try and guess an error. Okay, in the exam, of course, you just take the leap of faith. Just try, okay? You don't waste time to think. 122, never mind. I don't know whether got benzene ring or not. I just put in the benzene ring first. And then it turns out that the number is nice, 46. Then go ahead, all right, and try and figure out what 46 could be, all right? And it turns out that NO2 is the case. And after that, of course, then you can deduce the structure of B. Okay, so turns out the structure of B to be exactly what I said. So if you notice, this is the CH2 chain that I told you just now. Okay, then just now the 31, okay, the very first 31 is actually CH2OH, right? You just play with the atoms of N and O, you will be able to get this. And also, how do you know other functional group? Very simple, because once you know what is NO2 and there are 4 labile protons, there are only one way to make 4 labile protons out of the remaining oxygen and nitrogen. Because you have N2 and O4, and NO2 takes out 1 nitrogen and 2 oxygen. You are left with 1 nitrogen and you are left with 2 oxygen. And the only way you can get 4 labile protons out of this N and O is to get NO2 and OH, okay, 2 of the OH. So that's why you get this particular structure. And you already know the carbon chain of CH2 from the NMR. So you just need to put them in, all right? And you can obtain this structure, okay? Due to time, I'll leave it to you to figure out, all right, the exact details. Okay, I'll just give you the overview. Then after that, of course, you can find the answer. So I believe that you can draw either ester or amide, okay, by combining A and B. A has carboxylic acid, so that carboxylic acid, you can hydrolyze it either from the ester or the amide. So if your answer contains either the ester or the amide, it's fine, okay? All right, I think that alternative answer can be accepted. Okay, I'll move on to the last question that I have time to discuss, which is 6. 6A1 is recall, okay? If you cannot recall this, something you need to revise. 6A2 is also a recall, okay? Why is it a recall? Because in your syllabus, you are supposed to know for cases like HCl, H2O, of course Cl2 as well, or CO2. Okay, why are these cases discussed in the lecture notes? Because these are a bit of the representative cases. This represents a diatomic molecule, okay, with the same atom, all right? So this represents a molecule with 2 atoms, okay, that has some difference in electronegativity. What does H2O represent? The H2O represents a typical example of a 3-atom molecule, all right, that is not linear, okay, that is non-linear. So H2O represents that, all right, 3 atoms, 2 of the identical atom. So when you see this question of SO2 and OCS, you got to link back to the typical example that you see in your lecture notes. SO2 is non-linear, okay? All right, this is the common mistake that students always make. SO2 is non-linear, all right? So this non-linear SO2 looks very similar to the H2O that's being discussed in the lecture notes, all right? So you just need to discuss the same way, all right? So you need to link to what you have learned. Now, what does CO2 represent? CO2 represents a 3-atom molecule that is linear, okay? CO2 represents the 3-atom molecule that is linear. So OCS is linear. If you draw the Lewis structure, the carbon only has 4 electrons, so there's no lone pair on the carbon, so it is linear. So the only difference between this and the CO2 is that it is not symmetrical. CO2 is symmetrical, so therefore in CO2 the symmetric stretch do not contribute to the IR absorption, whereas in OCS, because it is not symmetrical, so when you have symmetric stretch, all right, you get a change in the dipole moment, so there is a absorption, all right, there is an absorption for the symmetric stretch. So therefore, all right, it has one more absorption compared to CO2. Okay, so that is something for you to think about. All right. Okay, of course, you can go home and try and figure out this part. Okay, again. Okay, let me scroll this. Okay, so continue. This part you can go home and read. Okay, I think I'm more concerned about part B and C. Okay, so part B. Okay, so in part B, you see this question, you cannot make your own assumption. You just have to follow, okay, what the question wants you to do, okay? Because if you start to make your own assumption and try to force it on this question, you will get the wrong answer. In fact, when I set this question, I also purposely make this diagram nice for you, okay, to have the anti-periplanar, all right, to hint to you that this only produces one of the product. Okay, if you have this, in this case, like the H and this leaving group on the exact opposite side, which is anti-periplanar, if you imagine this H is gone, this leaving group is also gone, what product will you get? You will get D as the product. Okay, why? Because the pH and the H is on the same side, whereas the isobutyl and the deuterium, all right, is actually on the same side as well. So you get D. Then the question never say you get another molecule to get E. The question says that this same molecule C gives E. So you don't anyhow and create another molecule and force it to produce E. No, the question says C undergoes elimination to give two possible products of D and E. All right. So you must start with C. So how C can get E? Okay. So you got to consider another possibility. All right. And of course, that possibility is in your syllabus. It's called syn elimination. Okay. So what happened is that if you rotate this bond, the single bond, all right, and if you rotate it with the leaving group now pointing up, so instead of this, so let me just draw it out very quickly. So this is H, and then the nitrogen leaving group is on top. Okay, so here is still the same, all right, and then the pH is still the same. Then because of the rotation, the H is now on the outside. Okay, the H is now on the outside, and the D is now inside. Okay, so if you rotate the leaving group such that the H and the N is now on the same plane again, so then you get this. All right, and if you eliminate the leaving group and eliminate the H, all right, you will get product E. Okay, so that's how the product E is obtained. All right, so C gives both product D and product E. All right, one is through anti, one is through syn elimination. Okay, so that is the point. So once you are clear on that, I think the question should not be difficult, okay, for you to do. I'll skip those parts that are easier. So therefore, in part 3, right, okay, draw the Newman projection to illustrate the conformation that is required for the E2. All right. So again, emphasize C produces both D and E. That means you got to rotate C, okay, along the C1 and C2 so that when the elimination occur, you get either product D or product E. Okay, so it turns out that for product D, you have this staggered conformation, and you get the product E, you rotate the bond such that the leaving group, okay, and the H, all right, is on the same plane. So this becomes a syn elimination. This is the only way where you can get this, right? And the hint is, of course, in part 2. The leaving group and the proton must be on the same plane. and there are two ways that it can be on the same plane. This is on the same plane, all right? So you can have the anti-same plane, or you can have the syn same plane, all right? Okay, and both of them can give elimination product, which is actually discussed in your lecture notes. Okay, then of course explain why E is higher U than D. So then you cannot force yourself to against the data. The data tells you that E, even though it is a eclipse conformation, it gives a higher yield of product. So you just have to explain it based on what data tells you. All right. So of course, then you try and figure out and realize that, oh, what makes this unstable is the gauge steric interaction here. All right, it's the steric interaction here between the two bulky groups. Whereas here, yes, it is eclipse. Yeah, it is eclipse. But then most of the eclipse interactions are with a small H atom. Okay. Whereas here you could have, imagine this big thing. So, I mean, on the drawing, it looks small. But if you think about it, this is an N with a C, and each C has a H. Okay. And then each C has a H. Okay. So everything will be steric there. All right. So it's not so stable. So that's why E is more stable conformer, even though it is an eclipse interaction, and therefore it gives a higher yield. All right. So based on the data, work around the explanation. All right. Don't try and force the explanation against the data that's given to you. All right. Okay. So part 5 is actually in your lecture notes. Okay. I think this was already discussed. Okay. So I'll leave it the details, but the main point is this. Okay. This can form a pair that is of the syn. Okay. This hydrogen is at an angle to the chlorine. All right. Don't try and think the hydrogen is like this. No, the hydrogen is not pointing to the top. The hydrogen is pointing to an angle. All right. So if you look along this bond, okay, the chlorine is at the bottom. The hydrogen is actually here. All right. It is not 180 degrees. Okay. It's actually around 120. All right. Okay. So therefore, they are not on the same plane. There's no anti, there's no syn. So elimination is harder to occur. Whereas this one, all right, if you draw the Newman, okay, the Cl is like this, the H is also like this, all right. They are in actually 0 degrees of dihedral angle, so they are on the same plane. So syn elimination can happen, all right. Okay, 10 minutes for the last question. Very good. Okay, or rather the part C, where many students, okay, were I received feedback that this question was a bit of a challenge for many people. So how do you interpret this diagram? All right. So you got to read, of course, the preamble. All right, but I'll skip the preamble for now because we don't have time. We'll straight away dive into this diagram and I'll explain. And let me enter this. Okay, so how do you read this particular diagram? This diagram is actually a it is a flattened energy profile diagram. Okay, but okay, never mind. We don't need to concern about that. Let's just look at this. Okay, the questions gives you a very important hint, but you might not have picked up the hint because it is hidden. And by the time you reach this question, you already panic. Okay, most likely that you will skip this part and then move on to other question. So changes in two critical bonds. All right. That is the main point how this graph or plot can be plotted. And we are talking about elimination reaction. So where are the two critical bonds in the elimination reaction? Let's do a very simple example. All right. So if you have, let's say, a Cl and a H, and you want to form a CC double bond in between, there are two critical bonds that you need to break. First is the CH bond. Second is the CCl bond. All right. And this is taken away by a base, okay? So a base might be taking this H away. So this is the deprotonation part, okay? This is the leaving group, okay? So means that in the elimination reaction, when you form a CC double bond, all right, you are breaking two critical bonds. One is the leaving group, one is the deprotonation, all right? So then how these bonds are broken, okay, will depend on the particular pathway or mechanism that it undergoes. So let's say for E2 elimination, the breaking of the two critical bonds happens at the same time. happens at the same time. All right. But for the E1, let's say, the leaving group will break first. So the bond of the leaving group will break first, and then the deprotonation comes in later. All right. So the bond of the leaving group will break first, form the carbocation, and then the leaving group will come later. So that is illustrated in this particular plot. So if you see this particular plot, right, the axis is what? Extent of leaving group departure, and here is the extent of deprotonation. All right. Okay. So extent of leaving group departure and the extent of deprotonation. So therefore, what it means is that it is trying to plot how the bonds are broken. Is it breaking at the same time, or is it one is breaking more than the others? So that's why if you look at the middle 1 to 4. So let's look at 1 to 4. Okay, straight away 1 to 4 through TS1. Okay, so what happens is that as you walk along this path, the extent of leaving group breaking away and the extent of deprotonation happens together. So that is clearly E2, which is what I've illustrated just now, right? So again, let me put this here. Okay, so if the extent of the leaving group breakage and the extent of deprotonation happens together, it is an E2. Now, let's look the other path. If you take this path, you realize that as you take this path, your extent of leaving group leaving is getting larger and larger, but the extent of deprotonation remains 0. That means only the leaving group bond is broken as you go down this pathway to reach 3, but there's no deprotonation happening yet. So it means what? It means that this part, the leaving group leaves first. So that's why you form a carbocation. After that, in order to reach the product, you go through this pathway where the deprotonation happens more and more and more until you reach the product. So it's like after you form the carbocation, the base take the proton away. So this pathway of 1, 3, 4 represents an E1 pathway, okay, where the leaving group leaves first until you reach this intermediate. After that, the deprotonation happens, all right, and then you get the product. So this is how you should be interpreting and reading this diagram, okay, all right. So based on this 2-chloroethyl benzene, okay, example, all right, so and try and figure out. Okay, so therefore I've answered part of the question below. Okay, so I've answered this question already. Why that is an E1? Because as you come down from here, the leaving group leaves first. There's no deprotonation until the leaving group completely leaves. You get a carbocation. Then you get deprotonation. So it's typically what E1 is about. All right. Okay. So nothing too special. Okay. Then part 2. All right. So the transition state for this is given for 2-chloroethyl benzene. Okay. Then the question is actually asking you what if you have 1-chloroethyl benzene. Okay. So if you compare the two molecules, so if I have 1-chloroethyl benzene, all right, it will look something like this. Okay. So this is 1-chloroethyl benzene, and I want to form a double bond. Okay. So what happened is that I must either break this leaving group or break this hydrogen. Okay. So then the question is the TS shifted from TS1 to TS2. So state the effect on extent of leaving group departure and extent of deprotonation. All right. And briefly explain your answer. So based on the plot just now, okay, I'll go back to the plot later. Let's look at this. So what happened? What happened is that let's consider both. Okay, let's consider this case where the leaving group leaves first. Look at this. When the leaving group leaves, it forms a delta plus on the carbon. When the proton leaves, it forms a delta minus on the carbon. So when this leaves, when this is broken, it will form a delta plus on this chlorine. And when the chlorine completely leaves, it will form a carbocation. All right. So it means it will form a carbocation, okay, like this. And this carbocation is very good. Why? Because this carbocation can delocalize into the benzene ring. Okay, so this process is actually favorable because by having the leaving group leaves first, it forms a carboxyl ion, and that carboxyl ion can be stabilized to resonance from the benzene. Whereas if let's say we keep the leaving group and we make the hydrogen leaves first, so we keep the Cl and we make the hydrogen leaves first, right? It will form a lone pair there. You'll form a negative charge there, all right? Because the hydrogen is taken away, of course, then you will leave a conjugate, right? So then you realize that there's no way that negative charge can be stabilized, all right? Or rather, it's not as effective as the stabilization of the carboxyl ion. So it means what? It means that if the molecule changes to 1-chloroethyl benzene, all right, the leaving group, the extent of leaving group leaving will increase, right? Will be preferred, whereas the deprotonation will be not so preferred. So that is the conclusion based on the structure of the molecule. And true enough, okay, of course, if you look at the diagram itself, all right, what happened is that when the TS2 goes to TS1, what happened is the extent of deprotonation has decreases, all right, so has decreased, whereas the extent of the leaving group departure has increased. Okay, so it is proven. Okay, or of course you can look at this first and then try and deduce the reason why the leaving group departure is favorable, all right, and why the extent of deprotonation has decreased. Okay, of course, it's due to the stabilization of the charges. Okay, 601 already, all right. So I think with that, you will be able to actually figure out the others. So it's all about, the main point is this, it's all about when the leaving group leaves, it forms a delta plus. When this one leaves, proton leaves, it forms a delta minus. So the ultimate intermediate is either a carbocation ion or carbanion. Whatever factor that can stabilize those charges, that process will be favored. All right. Okay, and that process will be favorable. Okay, in this plot. Okay, so I'll upload the answer, or rather the answer should have been uploaded already on the Google Classroom. So you can check it, and also the examiner's report. It will be very useful because it has all the comments of the markers for these questions, all right, when we mark this question back then. Okay, so that's all for today. So the tutors will distribute on my class also. Please distribute the extra practices. Those practices are for you to practice before the actual prelim exam, all right? So we will not discuss those questions, but feel free to ask us, okay, or consult us, all right, of those extra practice sets. Okay, so those are really for you to practice before your actual prelim exam. All right, we will not have any more lesson until after prelim. Okay, so all the best to you for your prelim exam. All right, study hard, study smart. Okay, and yeah, as I said, give yourselves time to digest the content material. Okay, that's all. Thank you.